Hello, hello. Yes. How's this? Okay, yeah, thanks for being here. So let's continue on DSP, right? Yeah. Um, what do we have? Want to see this? Yeah. Okay, yeah. So a bit of a recap. We are finally about to finish our discussion on FIR filter design. Okay. So there are two main ways to design an FIR filter. One is by window. Okay. So using a window to multiply your ideal response, and you will get an FIR. Yeah. And particularly we talk about type 1. So a bit of a recap. Type 1 FIR. So we focus on symmetric, evenly symmetric filters in the time domain. So type 1 filter is a kind of filter which start at time 0 and then end at the last non-zero sample with time m, where m is an even integer. Okay? M equals to 2n. So the middle line is right here, half of m. So the middle line really is when time index small n is equal to big N. Yeah. And then we would require the filter to have a kind of symmetry, so that let me try to you know what I mean. So it's going to be symmetric around the middle line. So that's type 1. Yeah. So we write h of big M minus n equals to h of n for all n, for from 0 to big M. That's where we have non-zero samples. So it's finite impulse response in that regard. So F1, the type 1 FIR filter. And that's how where our focus is. So I said that there are two major ways of designing FIR filter. One is by using a window. And the second kind, which we started last week, is called optimal design. So the design of our filter has to satisfy certain optimal criteria. Okay, 一些最佳性的一些的条件啊。So that's what we were at last time. So we formulate FIR design as an optimal approximation problem. And in that problem, we would minimize some kind of error, some kind of objective function. Okay, we want to minimize the error, so to speak, but in what sense? In the min-max sense. We minimize the maximum approximation error in stop band and also as well in the pass band. So we need to take a look of the objective function. So here is the formulation. Just to make our discussion a bit easier, let's assume that really we have this we assume that h this type 1 is 0 phase. Yeah, so it doesn't really affect the results, so we can just redefine time 0 as the middle line. Okay, let's just make our life simpler. Because if we do this define and just allow the time index to go negative, then we have h of minus n equals to h of n. That's a 0 phase definition. Redefine our time 0 to redefine the middle line as our time 0. That will make our discussion much easier. Why? Because when you do the Fourier transform, then everything in the frequency domain is going to be real valued. So it's making our life easier. Equivalent. Okay. Once you have this design, you can make it causal by shifting everything to the right. So this is just a simplification which makes our life easier. It makes it easier for our discussion. Okay, so if you agree, let's just agree that we will have this constraint where we have evenly, we're focusing on the kind of filter where the impulse response in time domain is evenly symmetric around time 0. Around time 0. Okay, so sounds good. Are you with me so far? Yeah, making this simplification. Okay, yeah. Yeah, so we design with this constraint. 它是一个限制条件啊。We design with this constraint 限制条件。And then we just quickly realize that then the frequency response is going to be this is the frequency response, right? The symbol. And if you just use the definition of DTFT, you get this result. Everything's real values as we promised, right? As we know this. H0 in the middle, and we have 2 times the summation of coefficients times cosine omega n. Okay, just according to definition of DTFT. And in general, it's a real value. It's going to be a real value function of small omega. And we have this notation. And so the scenario will be, for example, if we are now designing a low-pass filter with stop band and pass band. Let's say the pass band has a color frequency like that, and the pass band we wanted the gains to be unity, to be 1. Okay, seen this over and over again, many times now. So now we also have the edge frequency for the stop band. We start here, and the desired response should be 0 until Nyquist rate at frequency pi. So that's our ideal response. So now, if we just denote our ideal response with still h desired. Yeah, I should just bear with me. Let's just write it as a function of omega. There really is no need to write ej omega right here. Okay, so it's easier if we just denote our ideal, the desired, 想要的, desired response as using that. So this is our response, ideal, desired response in the frequency domain for the pass band as well as for the stop band. Okay. Then we define a weighted error function. Weighted error function, subtract your design. This is something that we are going to design by choosing all the coefficients in a clever way. We are going to design these coefficients, but subject to the criteria that we in some sense minimize this weighted error. Minimize this weighted error in the minimax sense. So we are going to minimize what? Minimize the maximum weighted approximation error. Minimizing the maximum. So that's what's special about this problem. Okay, we are minimizing the maximum weighted error with absolute value right here. Yeah, so that's kind of a general formulation. And in the next page, we introduce that we actually turns out that to formulate the problem is easier to make a change of variable like that. Yeah. So last time we suggested that we are going to, this is what we're going to do. We're going to change the variable from omega to x, from the omega domain to the x domain, if you will. So if you simply define x equals to cosine omega, then you get that x is going to be in this range from -1 to 1, right? Because cosine is bounded within -1 and 1. Yeah. Agree? Yeah. So x equals cosine omega, x equals to cosine omega from 0 to pi. So 0 frequency now becomes x equals to 1, and at pi over 2 is crossing, we all know that this is cosine, right? X equals to cosine omega. So we suggest that we make this change of variable. Okay, change of variable. So you can quickly see that there's a 1-to-1 correspondence between omega and x. 1:1的对应, 1-to-1 correspondence between omega and x. Okay, it's just a change of variable. But after the change of variable, it turns out that then what? Then any a of omega can be reformulated as a polynomial of x. So we should take a closer look, okay? So a of omega is by definition this DTFT of the frequency response, right? And it turns out that with that change of variable, then a can be reformulated as a polynomial of x, okay? Yeah. And there's a remark I'm making right here. So the key step is to understand that, to observe that, hey, cosine n times omega can be written as a polynomial of cosine omega. For example, cosine, we denote it as Tn cosine omega, where T, this is called the nth order Chebyshev polynomial. For example, T2x will be 2x 平方 2x squared minus 1 2x 平方 minus 1 which means, what does that mean? That means cosine 2x equals to 2 cosine squared x minus 1. That's the meaning. It's fairly easy, okay? It's a matter of definition, right? But with this understanding, then in general, it's true that cosine n times omega can be written as an nth order polynomial of cosine omega. You can go on. So next one, T3x. What is T3x? T3x, for example, T3x, we need to consider cosine. Then what you need to consider is what is cosine 3 omega? Cosine 3 omega is 4 cosine omega minus 3. Cool. I remember this is what I remember. Therefore, T3, just changing the variable, we have T3x, x is cosine omega, right? T3 is 4x minus 3x to the third power, cubic, okay? And so on and so forth. So every cosine m times omega can be written as an nth order polynomial of cosine omega. This is as a simple matter of fact, okay? And we call them Chebyshev polynomials. Okay, so far so good. So this is a key kind of intermediate step. 中间步骤，它有一个重要的中间步骤。It's a key intermediate step which allows us to always write a omega into a polynomial, no matter what your a omega is. As long as it satisfies this expression, we know that it's doable. Okay. So now finally, with the same optimality thinking, okay, we are minimizing, remember that we're minimizing the maximum approximation error. Within what? Within an intersection, within the intersection, not intersection, I'm sorry, 不是交接，是连接. We are going to, let me just read this first. We are going to find an argument which minimizes the maximum weighted approximation error. So just read this. We are going to find an argument. What do you mean an argument? Argument is the thing. Yes. 4 扣3减3扣，好，写错了对，谢谢。Summer is coming. I'm dizzy. 我有点头昏了啊。4扣3减3扣就哪个样？而且你们不是用这个口诀吗？Is it? Yeah. must have been around since the time of, I don't know, Laplace. Since the time when math is first introduced to Taiwan. Okay. Sorry about that. That's a obvious mistake. Okay. So wait. So is it 3? But you know what I mean. Yeah. Is actually there in this whole. I think tomorrow we'll discuss. In general, there is an iterative formula for us to derive what t of n plus 1, the n plus 1th order, the next polynomial, the next Chebyshev polynomial can be written as a sort of a combination of the previous two polynomials. We'll do that tomorrow, okay? Yeah. So you'll be able to, yeah, thank you for the correction. Okay, yeah, very good. Yeah, we are still awake. So now, this is about optimization, using the idea of trying to find a polynomial among any nth order polynomial or lower order, okay? PNR, that's a linear algebra notation, okay? This denotes the set. Did I write it somewhere? Okay, I didn't. I apologize for that. So that means that we are finding within the vector space of all the nth order polynomial, yeah, with real coefficient, okay? Or in the space of nth order polynomial, what's the dimensionality, right? What's the dimension of, how many dimensions are there? The space of all the nth order real coefficient polynomial has a dimension of m plus 1. Yeah, with also the constant term, right? We have n plus 1 coefficients to determine, so to speak. Okay? So anyway, so searching within that n plus 1 dimension space, find the polynomial which minimizes the maximum approximation in the sense that when you plug in, when you substitute px by your choice, yeah, you're designing px. Yeah. We're designing now in the x domain. Okay? Yeah. We're designing now in the x domain. Find the polynomial which minimizes the maximum approximation error among, this is a fancy way of writing it, s in cosine of the union of intervals. So I think in the previous page, let me jump back one page, this slide. So now, F denotes a union of passbands and stopbands. Okay, so in our case, in this case, the F, in omega domain is the union of our passband and stopband. So that's F. It's a set, it's a subset of the frequency range, of the entire frequency range. Okay? So now in the next page, I denote the kind of the interval of our interest now because I'm just writing it as cosine of this set. Yeah, the mapping F with the cosine function. Now it becomes a union of intervals in the x domain. Okay, so it's fairly easy. So let me explain. Now our concern is now going from omega to x. So let's just be aware that now number 1, x equals to 1. This point corresponds to DC frequency. This is low frequency to your right and high frequency to your left now. The order is reversed. The order is reversed. You get that? Yeah, because it's a monotonically decreasing function. Okay? Yeah. So now this is high frequency. No, this is DC. DC frequency. And the -1 is your Nyquist. This is x. And just in omega, now this is corresponds to pi. This corresponds to 0. That's omega. Okay? But otherwise, x and omega has a 1-to-1 mapping, right? So now, if we consider the passband, how does passband look like in this figure? The passband would be an interval, okay, from 1 to, let's say, here. We have the kind of edge frequency for the passband in the x domain. Yeah, And the stop band just continues, from, let me just draw it, emphasize that they need to be, they can be different, okay? Let's say this is pi. No, this is -1, okay? Just stretch my plot a bit further to my left. 画长一点啊 0 pi. So, and now this is our stop band in the high frequency range. Is that clear? Yeah. So stop band right here, pass band right here. But now we desire our response. So we desire our, since we're designing a low pass, right? So now the ideal response should be 1 in the pass band and 0 in the stop band. Right? That becomes our ideal response. So this ideal response now is denoted as somehow as in the textbook as dpx. Desired response in this example of designing a low-pass filter, the desired response should be 1 in the pass band and 0 in the stop band, like that. Okay, yeah. So now, this when we cosine f, this is simply a kind of sloppy way of just calling the union of these two intervals 它们的连集了 union. So it's -1 to the edge frequency in the x domain for stop band, as well as the other interval that's the pass band. So that's what I mean. This symbol, cosine of f, cosine of a set is a set in the x on the x line, x-axis. So far, so good. So we are trying to find the polynomial. That's our task. Our task is to find a polynomial with this nice property, which minimizes the maximum weighted approximation error within this range of x, within this range and that range. We want to minimize the maximum approximation error. Minimizing maximum approximation. For example, let's say if you just tried a polynomial. Sure, you try polynomial and the resulting plot in here might be like that. Let's say like that. That's your polynomial. Okay? Yeah. Why not? Yeah. Let's say you find the polynomial, and then let's try to figure out what is the maximum approximation error with absolute value. Okay. Just for simplicity, let's assume that the weight is everywhere is 1. Okay. Let's assume that weight is 1 in the pass band and 1 also for the stop band. Okay. So then here, really, when we take a look, okay, so now if this is p of x, then the maximum approximation error. So if you just take a look, wow, it seems that this is where we have the maximum approximation error, right? Right at the edge, right here. That's where the maximum approximation error occurs. It's even larger than this approximation error, right? No, no. Yeah. Yeah, it's pretty clear. Can we all agree that this is where our maximum approximation error occurs in when we consider both the pass band and the stop band? This is where the maximum approximation occurs. Okay, maximum approximation error occurs. Can we all agree on that? Yeah, with my random plot. Yeah. So for example, now this is the maximum of approximation error. Maximum approximation error of dp minus px. Okay. This is where it occurs. And if you just choose another polynomial, you get a different maximum approximation error. Okay. You change to just another polynomial, you get the maximum approximation error. So the maximum approximation error is associated with every choice of your polynomial. And now we are trying to minimize this error. Okay? Among all the possible choices of polynomials in the vector space, of nth order polynomials. Okay? Find the one. We want to find the one which minimizes this error, which minimizes its maximum approximation error when we consider both the passband and the stop band. Is that clear? Is that clear? Yeah. Reformulating into a polynomial approximation problem 会变成一个多项式逼近的一个问题啊。Polynomial approximation problem. So that's what we started the topic that we started last time. Then today we are going to go through this. So last time in the end we mentioned this. There's an alternation theorem. Okay? Alternation theorem, which tells us that when we solve this polynomial approximation error in the minimax sense, finding the argument which minimizes the maximum weighted error, turns out that there's a unique polynomial to any such kind of problem. Okay, there is a unique optimal polynomial with a hat. So this is fairly typical. Typically, we denote the best solution as using the hat notation. 戴个帽子啊 hat 戴个帽子在这边 yeah. So this best approximation has to satisfy a condition, and this condition actually is necessary and sufficient. Okay, there's a necessary and sufficient condition for this unique optimal solution, in that there exists at least n plus 2 value of x, namely x1, x2, all the way to x of sub n plus 2. There exists at least n plus 2. Actually, in fact, at most n plus 3. Okay. But now the theorem goes that there exists at least n plus 2 different x, different values of x, distinct, okay, different. Such that the approximation error, of course with weighting, okay, so this is weighting, such that when you go through all the points, at one point the approximation error is positive and the next one should be negative. Positive, negative, alternate. That's why this theorem is called alternation. 交错的交错的定理交错定理 alternation, alternate, alternation. Meaning that the error right here at one point is positive, but the next point should be one point is positive, next point should be negative, and the next point should jump back to positive, alternating in this regard. 这个意思啊 Yeah. And such n plus 2 distinct values of x exist. Not only does the error alternate, but also at these n plus 2 places, they all equal to plus or minus that maximum error that we are trying to find out. So the maximum error, or so can we say that the maximum error is achieved simultaneously at least n plus 2 distinct values. 然后再转一下啊。Are you getting it? Are you getting it? Are we getting it? 有感觉到吗？这是什么意思啊？ This is theorem, so it guarantees that it doesn't tell us, but anyway, this theorem does not tell us how to find the optimal solution. But we know, but somehow people know, yeah. People found out that it's a property of that optimal solution. The optimal solution has to satisfy this property. You need to, there exist at least n plus 2 distinct, should I say, points where the approximation error is maximized. It's simultaneously maximized. So that's a property. The optimal solution has to have at least n plus 2 points where the maximum error is simultaneously satisfied. And moreover, the error is positive at one point, negative at the next point, and the sign alternate between positive or negative of this maximum approximation error. It will be clearer in the next slide when we see a few examples. Okay, so as I promised, so this theorem does not tell us how to find it. That's another business. Okay, it does not tell us yet how to find the optimal solution, but the optimal solution has to possess 拥有 to possess this property. Possession. Okay, so let's take a look. It might be easier when we visualize what's going on. We need to visualize what's going on. Okay, so let's see a few plots. So here are a few examples. Okay, So now assume that we are designing a high-pass filter with pass band right here, stop band right there. Okay, now this is a high-pass filter. And now let's say we have an example of quite a few, of 3 polynomials. Okay, 3 polynomials, and it seems that, can anybody suggest that what's the order of a polynomial? 这是几次多样式的 ？1, 2, 3, 4, 4 extrema. 有4个极值啦，for extrema. Let me write it down. There are a few terminology that we need to use. So now in that example, it seems that we have 4 extrema. 有4个极值 So it seems that these are 5th order polynomial. Okay, did I write it somewhere? No, I didn't. But anyway, so you can find the plot in the textbook. Okay, it's in chapter 7. So these are a few examples of 5th order polynomial. Okay, so we have n equals to 5. N equals to 5, and or is it L? The previous page. Let me see. What's my notation? N. The order of polynomial is n. Okay, so now it seems that if you agree that in this next page n equals to 5, okay, n equals to 5, so n plus 2 equals to 7. So we want to examine how many alternating points do we have. How many alternating points do we have? And they're marked by the circle, okay? So here, alternating point means that the approximation error is they are going to reach the maximum error simultaneously. The alternating points reach the maximum approximation error simultaneously, and the sign of the error must alternate from one point to the next. 正负要交错. 2 criteria, right? So here in this plot, that's an extreme point where the approximation error reaches locally maximum, going negative. So this is negative error, positive error, negative error right here, positive error right there, and negative error right there, maximum. And the error reaches maximum simultaneously in at least 1, 2, 3, 4, 5 points. That's what we mean by alternation, as well as how do we define alternating points. Okay? Find the locations where the maximum approximation error is reached. Is that clear? No, 5 alternating points. But how about this one? This one is a local maximum, but the error does not reach maximum. The gain is locally maximum, which introduces an error of this much. Okay, but that error is not equal to these error right here. These are where the error reaches local maximum with alternating signs. Okay, so this one, can we count it as an alternating point? Can we? No, we cannot. Is that clear? So that's why this one cannot be counted as an alternating point. Is that clear? Yeah, because the error there simply isn't big enough. It's not the biggest. Okay, the error there does not reach the maximum. So this one right here, this local maximum right here, cannot be called an alternating point. Is that clear? Yeah. So 有点感觉哈。But how about this one? According to this plot, does the error reach the absolute value of the error? Does it reach the maximum right here, right at the edge, right at DC? Is the error maximum? Yes or no? Yes or no? Yes, right? But this point cannot be counted as an alternating point. Why not? Because the previous point has a negative error. And this point also has a negative error. So the sign does not alternate. They have the same sign, so sorry, this one, even though we look at your error, yeah, it's maximum, but this point cannot be counted as an alternating point because the sign needs to alternate between negative, positive, negative, positive, negative. No, this one is also negative, so if the sign does not alternate right here, this point cannot be called an alternating point. So that's the way we count how many alternating points there are. Okay? Yeah. Any question right here? Is it clear? Is it making sense? It makes sense, huh? So all about what counts as an alternating point. 那个交错点要怎么定义啦？就手一扣一交错点 alternating points. Okay. So to summarize, in this plot, we have a fifth order polynomial, and we have 1, 2, 3, 4, 5. 5 alternating points. Therefore, this polynomial does not satisfy the optimality criterion. Does not. Because of the criteria, the necessary and sufficient condition. Okay, the sufficient condition goes that we need to have at least n plus 2. N is 5. The number of alternating points is also 5. It's not n plus 2. It's not 7. We don't have as many as 7 alternating points. So therefore, by applying the theorem, we can conclude that this polynomial is not optimal yet. It's not an optimal approximation of our frequency response yet. It's quite good, but it's not yet the best. Is that clear? Yeah. Yeah, it's getting there. Yeah, it's getting there with passband and stopband. It's getting there, but it's not yet optimal. 这样有感觉吗？ It's getting there, but it's not yet optimal. No. So now let's look at part C. Okay, so in this part C, what do we see? Let's focus on part C now. Yeah. Now in this example, we have 1, 2, 3, 4, 5, 6, 7, 8 places where the error reaches maximum. 8 places. So that's one thing to notice. And second thing to notice is that we want to ask the question, do they have alternating sign in terms of their error? And yes, it turns out that the answer is also yes. Yeah. We have positive, negative, or maybe I should say going above, going below. Okay, going above, going below, going above, below. And then the next point is also above, right? Above, below. Yeah, the sign is alternating. That's great. That's the property we're looking for. Okay, with alternating sign of whether the error is going, whether the response is shooting over or going under. Okay, above, below. Yeah, the signs is alternating among the 8 points. And 8, what is 8? Is 8 big enough? The answer is yes. Yeah, we have at least n plus 2, right? So now this thing has actually more than n plus 2. That's okay. Yeah. So this unique solution has n plus, at least n plus 2. 1, 2, 3, 4, 5, that's n. 3 additional ones. 多了3个 n plus 3, that's fine. So this one, just as promised by the theorem, we can tell that this is the optimal fifth order polynomial. It should look like this. It should look like it has at least 7 alternating points. But in this case, we have 8. It's okay to have one more. All right? So let's complete our observation right here. Now coming back to this example, it's also not optimal yet. And why not? Because we have now 1, 2, 3, 4, 5, only 5 alternating points. Not good enough. Okay, not good enough. With 1, 2, 3, and this point, again, the similar principle. Even though this point right here has reached maximum approximation error by going under, but the previous point is also going under, right? So under, so this one cannot be called an alternating point. The sign is the same, okay? It cannot be called an alternating point. So therefore, when we count with 1, 2, 3, this one doesn't count. The fourth one is right there with alternating approximation error sign, the sign going below, going above, okay? So 1, 2, 3, the fourth one right here, the last one right there. We don't have enough of the alternating points. Okay, we are looking for at least 7, right, for fifth order polynomials. Okay, so that's the idea. So this is the theorem. This is how how you evaluate. Okay, this is how you evaluate whether or not your design is optimal. Is it making sense? Is it making sense? Actually, if you take a look, so even without, let's say, forget about alternating theorem, okay? But before you learn that, let's say, imagine that now you're a high school student, okay? If I ask you, is this polynomial minimizing the maximum approximation yet? You probably see that there's still room to improve. There's still room to improve. Maybe you can slightly change the polynomial coefficients to make the error bigger right here, but smaller at everywhere else. Then you might be able, there's still room for improvement. Do you see what I'm saying? 有没有感觉? So even as a high school student, if you understand, okay, our goal is to minimize the maximum approximation error. It seems that there's still room to improve. You can write a very similar polynomial with maybe slightly larger. There's room, right? There's room. Right here, there's room. You can choose a very similar polynomial with slightly larger error right here, whereas everywhere the error is reduced, is suppressed further. There might be still room for improvement. So that's kind of an insight. The alternative theory is nothing but just translating our insight into a formal mathematical statement, okay, which can be proved, by the way. Okay? So can you see that there's still room? And there's also still room right here. Yeah, you can maybe just shift the curve a bit, squeeze it in, 把它挤进来一点点嘛, right? So that the error right here might increase while making the error elsewhere to further reduce. Okay, there might be room for improvement. There might be room for improvement here as well, because right here, room for improvement, right here, room for improvement. Okay, so that's kind of when you look at. I'd like to invite you to really take a long look at this figure. It tells you a lot of insight. Okay, it gives us a lot of insight. 有蛮多直觉可以从这个观察中产生啊。And particularly, this actually gave us an insight as to how to write a computer program to reach this optimal design. Okay, so this is important. So now we got the idea that when there's room for improvement, then maybe we need to refine our guess. Okay, so the next slide, I'm going to go through okay, what is this? we also need to take a look at this. Right? In general, so when we have now this one looks like 1, 2, 3, 4, 5, 6. 6 extreme, it looks like 7th order polynomials. Okay, so in 7th order polynomial, we are looking for 9, at least 9 alternating points, and which we do have 9, I believe, in this particular example. And by the way, in this example, they introduce weight factor. Okay, the weighting penalty factor. We penalize error more in the passband than in the stopband. Okay, so the stopband ripple can be larger. Passband ripple has to be smaller. So that's how a trick you can use. By defining the weight factor, you can just obtain, you can just, now you have the flexibility, 这种弹性, you have your choice to try to focus, to emphasize on passband rather than stopband, or the other way around. Penalty factor that we were talking, the weight factor. Okay, so now as you can see, the ripple here is larger for stopband, smaller for passband. The ripple, 这比较小啊. And let's count the alternating points again. Okay, so there's one, the first one with where the error reaches maximum right here. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm not sure, but anyway, we have 9. So this one might be an example of reaching optimality. Okay, this polynomial is an optimal 7th order polynomial which approximates our desired response right here with the passband and the stopband. Yeah. So that's good. This is a low-pass design. A low-pass design, and just weighted factor where the weighted error reaches 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm not sure about that, but at least 9. Okay, so this is an optimal design. Okay, so what time do we have? When we come back, so let me just read it before. In the next hour, we will explain how to find it, how to find the optimal solution. But let's summarize. The optimal approximation approach provide a unified framework for designing low-pass, high-pass, bandpass, band reject filters, and so on. You can actually define your desired response as long as you define a multiple bands. Okay, this one passband in the middle, you can arrange it. You have the freedom, and this approximation approach provides a unified framework for designing all such filters. It also gives us a flexibility, as I mentioned, to vary the tolerance level between different bands. You can penalize error more in one band than another band so as to ensure that your error is the smallest in where you care the most. Okay? If you care about the error the most, put a heavy weight, put a larger weight factor. Okay? There's such a flexibility which allows you to choose your tolerance level. But now, in the next hour, when we come back after the break, we are going to introduce how to search for the optimal design. Okay? And it involves what I call 3 R steps and 1 S step. The 3 R stand for random guess, and then you refine your guess, and then repeat, and refine and repeat and refine until the stopping criterion is met. Okay, 3 R and 1 S, and we will explain that after the break. Okay, so let's take a 10-minute break. Okay, so if you're interested, so yeah, we're about to start our second hour of lecture. But I posted a few MATLAB scripts. Did I do it this morning or last night? I forgot. Yeah, maybe this morning, or last night. So in the next hour, I'm going to show you, introduce to you an algorithm, okay, which involves the 3R and 1S. Random guess, refinement, repeat, and stopping criterion, okay? So at home, I try to implement the algorithm by myself from scratch, okay? I had some fun 2 days ago, so I was able to come up with my own implementation. So I'm gonna share that implementation. I shared already, I loaded my implementation to the class website, to e-class. So if you're interested, for those of you that have you don't have your computer with you, do you? 有谁有带电脑来的？啊，好像都没有带。But anyway, so I'm going to show you. I'm going to go through the code. So that's my own implementation based on 3R and 1S. Okay, 3R and 1S. Random guess, refine and repeat, and then there should be a stopping criterion. Okay. So let's take a last look of, yeah. So now this algorithm. Okay, shall we start? 好, yeah. Okay, so this algorithm has a name. It's called PM algorithm. Parks-McClellan algorithm, PM, or PM. 2 people. And this is my last slide. Okay, it's a long kind of a flow chart that we are looking at right here. Hopefully, this 有没有太小？这大小还可以吗？ Can people in the back see the lines right here? Can I enlarge it? Is there any way to enlarge this? Oh yeah, there is actually. Zoom in, zoom in. Okay, that's great. Yeah, we can zoom in. Okay, so let's take a look. So this algorithm, should I say, is inspired by the alternating theorem. Okay, the theorem, remember that the theorem tells us that in the end we want to find at least L plus 2 alternating points, right? So the kind of a smart thing is to suggest that let's guess where they are first. Now, just make your guess. Let's say if your target is this polynomial with passband and stopband, and just they only want to make a, yeah, you can make a guess. So, and by the way, the edge has to be alternating points. Okay, so we know at least 2 of them. The edge, you can, yeah, you realize. The edge right here, they have to be 2 of the alternating points. Okay, X is this stop band, pass band. Okay, but otherwise, let me make a guess. Can anybody tell me, suggest the order of polynomial? Yeah, tell me. Yeah, give me the order n. N equals to what? Yeah. For example, n equals to what? Yeah. Can anybody tell me only 3? Larger. Because 3 is too limited. You can have that's Damides. Okay. Yeah. Damides. More? 再高一点5这么客气啊。好吧，就5好，也是了5好，那就5。Okay, so now we need to guess where the 7, or at least 7 alternating points. Make a guess. So we already have 2, so we have 5 more to guess. That's the idea. Okay, actually 5 is pretty good for educational purpose. Okay, so I'm not gonna guess there must be 3 in here and 2 in here, right? Because this is more narrower, right? This is narrow. So let me guess the other 2 right here. 3 maybe right here. That's my guess. Yeah. Just make my guess. Pretty easy. So that's the first step already. Initial guess of L plus 2 extremal frequencies. Okay. Oh, by the way, you know X. Let's just call X frequency because we know XP is cosine omega P, XS is cosine omega S. Okay. Yeah. So we know we're designing a low-pass filter. I'm guessing that the 5 places. 5 plus 2, 7 places, 1, 2, 3, 4, 5, 6, 7. Okay, making a guess. And then this step is the trick. Okay, then you can, turns out that you can already, now if we say this is x1, x2, x3, this is x4. Okay, you know, x4, x5, x6, x7. So remember that our goal is to find, so now summation AK for each j, we must have P of xj, which is defined by k from 0 to 7, AK xj to the kth power. Need to approximate our desired response, right? That's the idea. Finding a polynomial which approximates our desired response. The desired response is dpx. Okay? Dpx is 0 for stopband, 1 for passband. And don't care in between. Okay? By the way, don't care. We have a don't care region in between. Okay? Hoping everything's fine, gonna be fine. Yeah. So dp of x. So let's say we want to have this minus dp of x nearly 0 with alternating error, right? So equals to plus or minus delta. That's the idea. Delta is the maximum of the approximation error. Okay, so you can write down 8 equations, like seven equations. Then you can quickly write down 7 equations. Okay, 7 equations, a set of 7 equations for, I'd say, for each j in 1, 2, 3 to 7. And then you have 7 equations. No. How many equations do we have? We have 7 equations. But how come we have? Oh yeah, 7. No, I'm sorry. 5th order. Yeah, this is wrong. 这里是5了啊。Right. So we have 7 equations and how many variables? 7 equations and how many variables? We need to find these, right? 7 equations and how many variables? 6. No, 7. This is also a variable. We don't know delta yet. So it's pretty tricky, right? So yeah, I'm glad you come here. It's very tricky. We have 6 coefficients to solve, as well as this delta is still unknown. We're just guessing where they are, and pretending and hoping that, and also kind of requiring the error unknown, which is known to alternate sign. Okay, to have an alternating sign between points. Okay, so that's a trick. This is a very beautiful trick right here. Plus or minus delta, depending on the first one is plus, the next one should be minus. Okay? So just to be exact, let's try to write down a few of equations, and you'll know what I mean. So for example, the first equation should be a0 x1, no x1. No. a0, that's a constant term, plus a1 x1 plus a2 x1 squared plus all the way to the 5th order coefficient right here unknown to the x1 to the 5th power equals to plus delta. That's the first equation. And second equation should be, now the sign should alternate. That's the second equation. Okay, so let's write down the second equation. A0 plus A1, x2 plus A2. When we evaluate the polynomial at x2 of your guess, you're guessing where it is, A5 x2 to the 5th power equals to a minus delta, which is also unknown. And so on and so forth. Okay, and so on and so forth. So in general, we're going to have a set of n plus 1 equations. No, n plus 2 equations with n plus 2 unknowns. So we can just organize all the terms right here. And by the way, I'm assuming that the weight factor, let's not worry about the weighting factor yet, okay? Because when the weight comes in, then these delta and those delta should be different. but let's pretend that the weight is equal everywhere, okay? So now, in general, you can write this as a set of 7 equations with all the unknowns. Listed right here, the unknowns are the coefficients, A0 all the way to A5, the 6 of them. Delta is also unknown. Yeah. I'm sorry. Let me write a few more. So delta minus delta, then 1, 2, 3, 4. The fifth one now need to approximate pass band. Okay, these are stop band. Okay, stop band plus or minus delta. In the pass band, so let me focus on this one. The fifth, this fifth place is already in the pass band. So now we have A0 plus A1, the fifth point of your guess, plus A2, the fifth point of our guess, plus A5 over there, x5 to the fifth power equal to what? Plus, minus, plus, minus, plus. But it's 1 plus delta. Okay? 1 plus delta for pass band. Okay, so on the right, we must have. So you can organize everything and be careful. So the last column should be -1 plus 1 minus 1 plus 1. 1, 2, 3, 4, 5, 6, 7 -1. Approximate the desired response is 0 for the pass band, for the stop band, and 1 for the pass band. So that's on the right. You have 7 equations and 7 variables, 7 unknowns. And here, the first row is 1, x1, x1 square, x1 to the fifth power 1, x2, x2 square, something like that, and 1, x, 1, 2, 3, 4, 7, x7 square, blah, blah, blah. Yeah. So roughly speaking, okay? This can be found in the textbook, but in principle, hopefully I have convinced you that by guessing first, by guessing where the extremal frequencies are, then we can write down 7 equations with 6 unknown coefficients plus 1 unknown, that is delta. The last unknown is delta. Okay? So this becomes a set of linear equations, right? Set of linear equations. So now, that's what is meant. Calculate the optimal delta. Okay, the delta now is found, right? But can be solved by solving this matrix problem. Okay, a set of linear equations are the second step right here on the plot. And then, so if you check in the textbook, the third step after calculating delta, then after calculating delta, then you find that you find the delta, but you also find that your guess is wrong. Okay, it's just guessing, right? So at first you're guessing where the extremal frequencies are, but since it's just a guess, that probably needs some refinement. So let me draw a picture. Let's say, okay, now delta is found right here. Delta is found, and we have positive right here, negative right here, positive right here, and this is delta for sure, and that's also delta. Okay, so now the resulting polynomial, 1, 2, 3, 4, 5, 6, 7, okay? But when you fit the polynomial, wait, is this even possible? Yeah. But when you fit the polynomial, you find that the actual extremum may be elsewhere. Yeah. 1, 2, 3, 4, 5. That cannot be right. What's going on? We have a fifth order polynomial, but we cannot have so many. Oh, I'm in trouble. Anyway, so it's wrong plot. 黄色带是错的啊。So maybe this really should be under. Okay, let me try. If this is under, yeah, this is going above, going under, going. That makes more sense. Going above, going under right here. Going above, going under. Okay, that makes more sense, right?1 2 3 4 5 6 7 7个。So I'm having difficulty. Anyway. Okay, so this is a bad plot, but I have a computer code I'm going to show you. But let me try to explain the idea, okay? So at first, we guess these are where where the extremal frequencies are. Okay? At first, this is our guess, right? Now, but turns out that the maximum error is not reached. Okay? If you draw this polynomial, you notice that here we have an even bigger error. At this point right here, that it has an even bigger error because it's the actual local minimum right here. Okay? The actual local minimum does not occur at where our guesses are. Yeah. And this one has an even larger approximation error right there, as well as the edge frequency. Right, the approximation error there is even larger. Yeah, and the approximation error here is even larger. Okay, so somehow we need to refine our guess. Now, okay, we need to refine our guess by the next step. Okay, so let's take a look. We need to find out exactly where the local maximum of the error occurred, actually. Okay, actually. Once you find out the polynomial by solving this equation, you need to refine the locations. Okay? You first guess the location, and that got to be wrong because it's just a random guess, right? So now we got to refine it by what? By finding where the local maximum of the error actually are. Okay? Find where they actually are. So we now refine our guess to maybe, okay, this should be the new x1. This should be the new x2. The new x2, this should be the new x3, the new x4 still here, new x5 should still have the edge frequency. The new x6 could be slightly different. The new x7 is right at the edge, okay? Now, we need to refine our guess and then repeat. And then hopefully the algorithm will converge. Hopefully, and wish for the convergence. Okay, is that clear? So the first is to random guess. And with your guess, you get a polynomial fitting by solving this equation. And then this polynomial will actually have maximum and local minimums actually will not occur at exactly where your guesses are. So you need to refine your guess with a new set of now refined guesses of where the extremal frequencies are, and then you can repeat. You can repeat and repeat and repeat, and hope that now we can talk about the stopping criteria. Okay, so the entire process will stop when the points don't move. When now they repeat the process and the new x3 is the old x3. Okay, New x2 is the old x2. When the extremal points do not move further, then that's when you know you can stop. Because that has meaning, okay? When these points don't move, that means that these points not only are extremal points, but also they have alternating approximation error according to this matrix. When the points don't move, this is beautiful result, okay? Beautiful thinking of this algorithm. That's where the beauty of this algorithm. I'm not telling you that this algorithm is guaranteed to converge, but when it converges, that means your points are not moving. That's our stopping criterion, right? The points are not moving, meaning that your guess of extremal points are actually, bingo, they really are the extremal points with alternating signs of the approximation error, plus or minus delta, as you write down right here, plus or minus, okay? So that means that eventually when the algorithm converges, it gives you a polynomial that simultaneously satisfies two criteria. One is alternating approximation error. The other is that those are the approximation error are indeed simultaneously reach the maximum. Okay, so let me just just look down right here. Okay, and there is a trick of handling the case of having one extra. Having more than L plus 2, you need to choose the best L plus 2. So those are details that has been figured out. And checking whether extremal points change. That's what I mean moving. If they effectively don't change, let's say if they change by 10 to the minus 7th power, that's too little. You can just effectively 等效, that's the points are not changing. So checking where the extremal points change. If you just regard them as unchanged, then you get a Beck's approximation numerically. This is a numerical algorithm, okay? Using convergence. But if the extremal points changed right here, then you just go back. You just refine your guess. Refine your list of extremal points, okay? You just refine your list of extremal point frequencies and then repeat the entire process. By solving this first, re-evaluate the extremal points and compare whether those extremal points changed. Yeah? So that's the textbook flowchart for the PM algorithm. The PM algorithm. So now I'm going to switch to my test PM, okay? And based on the same principle, 3R and 1S. But just let's take a look. So now I'm going to switch to my MATLAB. Can I enlarge this? Do I need to enlarge this? Maybe I should. Preference, font. Apply. That should be better. Yeah. Okay, so in this piece of code, I'm trying to implement the Parkes-McClellan algorithm from scratch. So first I define my cutoff frequency. The edge frequency to be 0.3 pi, 0.4 pi in the omega domain, and then immediately I make the change of variable to go from omega to x, okay? So now this is my initial guess, okay? I'm guessing, okay, this is actually 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is frequency I'm guessing, so this is gonna be a 7th order fitting polynomial. 7th order for polynomial fitting problem. I'm guessing, and just you realize that the edge frequencies, actually these two edge frequencies have to be two of the extremal frequencies, okay? But otherwise, I'm guessing that we have the 3 for the, this must be the pass band and 4 in the stop band. Okay, so this is my guess. Just random. 有问题吗? Are you raising your hand? No, okay, yeah. Initial guess, fair enough. And then, yeah, I'm going to again go from omega to x. And then now I'm preparing for the while loop, okay? Including that I'm preserving the memory space, I'm sorting my list of frequencies, and I set the tolerance. This is a tolerance where I would just examine to determine change or not, whether the extremal points after one round iteration, whether they change or not. This is my tolerance level, okay, which is currently set at 1 to the 10 to the minus 4th power, okay. I'm preserving space for a big matrix right here. This matrix is called big matrix. Big matrix is what? 9 by 9, okay. And I'm preserving my space of the solution. No, this is HD. What is HD? Must be HD is the desire. Is it? Should be the desire response. I forgot. Yeah, but anyway, I'm preserving memory space for the big matrix right here, and then start iteration. Okay, so let's take a look at the while loop. Any question regarding how the settings are defined? These parameters, but you can play with it. Now, next is my while loop, which really consists of a few parts. So the first top part right here, I'm filling in the big matrix. Okay, big matrix is 1 x1 x1 squared, so on, right? Filling the big matrix. Actually, I should pull this to the outside. I'm stupid. Oh no, I'm not stupid because x is updated. Okay, yeah. So once you make your guess, or every time you refine your guess of x, you need to fill this big matrix. Okay, so that's the correct thing to do. And the last term is minus 1 plus 1 minus 1 plus 1. So I don't need to do this all over. So this is stupid. This line is stupid. Okay, I should move it to the outside. But otherwise, from here, I'm setting the desired response. If it's the pass band, it's 1. If it's a stop band, it's 0. Setting your desired response right here. Stop band 0, pass band 1. Okay, that's our desired response. And the next one is to calculate the inverse. Okay, solving the set of linear equations. This is basically big matrix inverse times HD. That's a notation. This is A inverse B 的意思。Is that clear? Yeah. So solving I call the result the temporary coefficient. Is because I call it temporary because the coefficient in general is not right yet, right? Not right yet. But the temporary solution is right here. That's right here. That's maybe let me mark. This is your TMP coefficient. TMP coefficient right here, and this is big matrix. Big matrix. Coefficient, and this is HD. That's my naming of the variables. So now, delta is the last component. Okay, delta is the last component of temporary. I'm taking ABS right here. And now with that, so that's the first part. Just calculating the temporary solution, which might not be generally is not right, not good yet. But now I'm just making plots, and then next is the part where we need to refine our extremal points. Okay, we need to refine these x1 to x7. So how do I do that? When I need to refine, it's pretty easy. So I'm just trying to find where the 6 local extrema are. Okay, 7th order polynomial can have 6 extremal points at most. Okay, so I'm finding this by using derivation. I find the first derivation. I find dy over dx. Okay. If your polynomial is y of x, I'm trying to just calculate g of x, and then find its roots. Because extremal point indicates that the first derivative got to be 0 over there, over all those places. 一次微分等于零就是 the local 最大值最小值。So I'm using this concept of trying to find out the first derivative. So here, seriously, what do I do? Seriously, I find this polynomial, okay, which I name dy dx coefficient. So what I'm doing here is when we have p of x, then the y equals to tp of x. No. Then dy dx, of course, is p prime x. So I'm storing the coefficient of p prime x into this array right here. It's called dy dx, the coefficient of dy dx. So is this going to be a polynomial of a sixth order polynomial? Okay, sixth order polynomial. This is it's kind of tricky, but I figure out. Yeah, you can fairly easy because the derivative is going to be a1 plus 2 times a2x plus 3 times a3x squared and so on. Just taking the first derivative. Fairly easy. Once you figure out the coefficients for the first derivative polynomials, find their roots, find its roots. Because the roots should tell us where the extremal points are. The revised extremal points, where they are. Is that clear? Is that clear? Yeah. Okay, so now the question. If P is seventh order dy dx coefficient, and then I take roots, and if we are fortunate enough, it has 6 roots. This is a sixth order polynomial, so we have 6 roots, x1 to x6. Okay? And then I also note that I'm also just suggesting that both the edge frequencies should also be in the list of alternating points. Okay? So on one hand, we have 6 extremal points. On the other hand, we have 2 edge frequencies. 6 plus 2 equals to 8, okay? But we need at least 9. This is a 7th order, the space of 7th order polynomial. We need at least 9. So not enough yet. 6 plus 2 is not enough yet. Now, where are the 1 extra extremal place that we need to include? Possibly the terminal frequencies, okay? Either +1 or -1. Okay, so the next part of the code is trying to decide: do we include 1 or do we include -1? Okay, that's my next the goal of these few lines. These are trying to figure out whether we include endpoints 1 or -1. So I'm going to leave it to you to figure out what's going on right there, but it needs to be determined. And finally, when we determine whether it includes -1 or +1 or both, then we can finally sort our set of extremal points and replace the previous current, replace the current with a new. And then finally also increase the iterative number by 1, then we can make the comparison whether the new set of points and the previous set of points, do they move? Are they moving? If they're not, we can terminate. So that's why the while loop right here on top, on the very top, the while loop, the condition is looking for the maximum amount of move. When we compare all the points here, all the points there, 1 to 1, okay? If they don't move more than, if they move more than the tolerance, then we continue. So that means that if they don't move much, They don't move even, if the move is smaller than this tolerance, then we can stop. Okay, long story short. Okay, so that's my implementation for you to play with. But now, finally, I'm going to play it. Okay, I'm going to play it. No, I'm going to run it. Okay, so that's the result. It's coming out. Yeah, the result of this. So see, I'm guessing that this is my guess. 1, 2, 3, 4, 5, 6, 7. Wait. No, anyway, so you. 1, 2. Let me be careful. I might be guessing here. I forgot. But anyway, so by guessing, this is the first response I'm getting. Okay, with delta right here, this is bounded plus or minus delta right here, and 1 plus delta, 1 minus delta. Okay. So my guess is pretty wrong, right? My guess is pretty wrong. These are not extremal points yet. The actual extremal points are right here, right here, right here, there. There are 5 of them. Six. Well, the 6th one is probably outside. It's not even within this range. So my guess was wrong badly. Okay, pretty badly wrong. So now I'm going to hit the button. This is just iteration 1, okay? Heavily wrong. Now I revise my list. Like that, and then just repeat. Getting better, right? Is it getting better? Look at how beautiful they are already, surprisingly. This took me by surprise. But here, there's still room for, this is still pretty wrong, okay? The guess is still pretty wrong, okay? So what do? Revise our list with 1, 2, 3, 4, 5, 6 extremal points, plus 2 edge frequencies, plus either this one right here or that one right there. So that we have 9 equations, 9 unknowns to play with in the next round. Is it 9? You know what I mean? Okay, we have so we have exactly the same numbers of equations and unknowns. Yeah. So now I'm going to hit the button right one more time. Yeah. It's getting weird. Next one. Look, this one, miraculously, this one. Now in the 4th round, we already have this kind of beautiful result with still some room for update. Some room for refinement right here, not right exactly right yet, but the result is getting there, okay? Only merely after 4 rounds of iterations. 4 iterations, the result is still getting, you can feel that it's getting there. It's almost satisfying the alternating theorem. Not yet, but almost, right? So you want to guess how many more rounds do we need until the tolerance is met? How many more rounds? If we want the point to not move more than 10 to the minus 4. Ding, 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 ding. Ding, 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 E. If we want these frequencies to not move more than 1 分之一, how many more iterations are you guessing? Yeah, you want to make a guess? 你觉得还要再跑多少次？10次 ，OK， 还有那什么？10次。那就以这表决，认为低于10次举手啊。We don't need more than 10 rounds， 高于10次请举手。好，答案会揭晓。4啊，我们要开始。4 4 5 6 7 7 only 3 more. And this is the final result. This is in the X domain. And now I'm going back to the omega domain, okay? But this took me by surprise. I mean, I've never implemented this by myself. Okay, only this week in my more than 30 years of career. Seeing this surprise, it surprised me. Only 7 iterations. Already, these points do not move more than 1 over 10,000. 1分之一 are not moving more than that by 7 rounds. That took me by surprise. By the way, I was expecting something more than 20, right? But surprisingly, in 7 rounds, okay? So play with it. There might still be some bug because, So now play with it. But I want to explain. To go from X to omega domain is not that trivial. It's not that trivial. So that's kind of another point we need to go through, okay? We don't have time. Now you get a fairly nice polynomial. What you get right here is a fairly nice polynomial, but we need to go back to the omega domain. Go back to the impulse response and so on, because polynomial is not omega, right? Not in omega yet. So how do we make the conversion back to the omega domain? So by the way, this is the magnitude response as well as phase response. The magnitude response is in dB, okay? The usual way of plotting. So now the next step, we need to figure out how to go back to the omega domain. Okay? Given that we already know P of X, now we have a P hat of X. That's what the program is giving you. P hat equals to best solution A0 plus A1 X plus A is a 7. Is this seventh order polynomial X to 7. Has to somehow equal to A omega. What is A omega? A omega is X0 plus 2 times summation, right? K from 1 to 7, H of K cosine of, let me say just N, okay, H of N, yeah. Hn cosine of N omega. Somehow we need the equality. We need to go from X domain to omega domain by finding out the filter coefficients. These are the actual filter coefficients, right? Still need to find them out. But how do we do that? How do we do that? So we know that here is fairly easy. H0 and 2 times summation N. H of N, that's an unknown. But now, what is cosine N omega? Cosine N omega is T Chebyshev polynomial, right? Cosine already talked about that. Cosine N omega is a Chebyshev polynomial of cosine omega, okay? So here really is T, by definition, Tn of cosine omega. And what is cosine omega is X, okay? So H0 plus 2 times summation N from 1 to 7, Hn unknown, but we know that Hn is multiplied with Tn of X. And you know what Tn of X are, right? Where T0 is 1, T1, X is X, cosine X is cosine X, cosine 2X is 2 cosine squared minus 1, and so on, okay? So you can equate, you can just enforce equality between this expression and that expression. This is a polynomial, that's a polynomial, and by comparative coefficients, you can convert from A to H. Just quickly speaking, right? Now you can convert that. Okay, so this is doable. Well, I say it's doable. Okay, yeah. So maybe I can also tell you just indicate where in my code this part is. So here in the code, back in the code, the last part is right here. This is where I made the conversion back to the omega domain. Okay. First of all, I wrote this code which just returns Chebyshev polynomial up to the nth order. Yeah. And then I find out B. And then H is simply according to B. But here, be careful that in principle, you can just obtain H0 to H of N. Okay, obtain them. Please do that. But do not forget that the filter of your design, once you solve H0, actually, you might be able to take a look of H. Let's take a look of H. It's not. So that's H. But it has a middle point right here. That's H0 in the middle. H0 in the middle, H1, 2, 3, 4, 5, 6, 7. Okay, and it's symmetric on the other side. Okay, don't forget that you need to make it symmetric. Okay, there's H1, there's H minus 1. There's H2, there's H minus 2. And you need to put everything in a big array which has a length of 2n plus 1, right? To make it a type 1 filter. That's like one last step you don't want to forget, because I did. Two days ago, I made a mistake by forgetting to include the negative time part. So anyway, once you do that, you'll be able to get the frequency response right here, which looks sort of flat, and you have an equal ripple property. All the maximum approximation error are simultaneously met right here, 1, 2, 3, 4, 5, at 5 different locations in the stop band. So that's probably all I want to say for today, and that concludes all our discussion on FIR filter design. Okay, any comment? Do you want to see a few more examples of running the code? Just if you're really interested, please play with it. Okay, and I'm not sure because it's kind of running, but I'm not sure if there's still some bugs. And my method is slightly different. Let me also mention this before we leave. My method of refinement is slightly different from, it's quite different, I should say it's quite different from what's being suggested right here on this flowchart. Different, okay, in what? Different in which step? Let me try. In this step, okay? Remember that right here, when I get a polynomial, I'm trying to just literally derive its first derivative. It's doable, polynomial, easy, right? First derivative is pretty easy to calculate, and then finding root, But in the textbook, they don't suggest doing this. Okay? This is where my implementation differs from this flowchart. In the flowchart, if you are so interested, you can take a look. The textbook suggests that you should do interpolation instead of actually writing down this expression for the first derivative. Okay? They suggest that you should just interpolate and find numerically where the maximum errors are. Find local extrema. So the meanings that in the textbook, they are suggesting that once you plot a polynomial, you should just, they are plus or minus delta right here, right in your selected extremal points, right? It's getting busy, but hopefully, So they suggest that actually, once you know the polynomial value for a few points, then you can do Lagrange interpolation, basically, to figure out every other point continually. So they suggest that you should numerically just calculate all the polynomial value by interpolation, by numerical interpolation. That's where my implementation differs from the textbook. Okay, I'm not saying which one is better. Maybe, but I solve it differently. Okay, so I'll just want to point out that my implementation right here is different. And in the code, I'm not using interpolation. So one last thing to point out. So any question? All right, so hopefully you get to play with my code. And please tell me if you find any bug. Please tell me if you find any bug. Okay. So next week when we come back, we are going to change our topic to information retrieval using short-time Fourier transform. Okay, but that will be the end of our discussion on FIR and design of a digital filter. Okay, thank you for being here, and we'll see each other tomorrow. Okay, see you tomorrow. Thank you.